Beneath the earth, in darkness no human eye will ever see, something remarkable is happening right now. Atoms are drifting into place, one by one, forming perfect geometric patterns that have no designer, no blueprint, just the quiet laws of nature repeating themselves in the silent depths of stone. Tonight, we explore the hidden world of crystals, those glittering fragments of earth that have fascinated humanity since the first ancient hand reached down to pick up a sparkling stone from the riverbed. They are puzzles frozen in mineral, equations made visible, time itself turned solid and still. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will carry you through caverns of amethyst, forests of quartz, and oceans where crystals grow in living shells. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever held a crystal and wondered how such perfect shapes could emerge from chaos? You are not alone. If these quiet wonders bring you peace, consider leaving a like or subscribing so we can continue sharing this space together. Allow your shoulders to drop just a little. Notice the weight of your body against the surface beneath you. Let any tension in your jaw soften and breathe slowly, as if each breath were drawing you deeper into the stillness of crystal caves where nothing moves but time itself. Let us begin. A crystal is any solid whose atoms are arranged in a repeating pattern. When we think of crystals, we might imagine glittering gemstones or sharp edges of quartz, but the scientific definition is broader and includes substances we encounter every day without realizing their crystalline nature, from the salt in your kitchen to sugar dissolving in your tea. What makes a crystal is not its beauty or rarity, but the invisible order within, atoms and molecules locked into a precise three-dimensional grid that repeats in every direction, creating a structure as predictable as squares on a chessboard. This internal arrangement determines everything about the crystal, from how it reflects light to how it breaks, and it is why two crystals of the same substance will always form the same shape no matter where in the world they grow. Order arises from chaos. Nature builds perfection from simplicity. The word crystal comes from the Greek word for ice. The ancient Greeks, gazing at the clear perfection of quartz, believed they were looking at ice that had frozen so completely it could never melt, and they named it kristallos, their word for ice, a term that evolved into our modern word crystal. This beautiful misconception persisted for centuries, a testament to how convincingly quartz mimics the appearance of frozen water with its transparent clarity and cold, glassy surface that feels cool to touch. The error was understandable because quartz is found high in mountains where snow and ice abound, and the Greeks had no way of knowing this gleaming mineral forms not from water, but from silicon and oxygen bonded under tremendous heat and pressure deep within the earth. Language preserves old beliefs. We still say crystal even though we know it was never ice. Ancient Greeks believed quartz was ice frozen so deeply it could never melt. This theory, known as the perpetual ice hypothesis, held that quartz formed in the coldest regions of the Alps, where winter was so severe that water froze into a state beyond ordinary ice, becoming a permanent solid that no heat could liquefy, a substance caught between water and stone. Philosophers debated this idea for generations, and it was not until the 17th century that scientists finally proved through careful experiments that quartz would not melt at any temperature achievable in their furnaces, and that its composition was entirely different from frozen water. The persistence of this belief shows how powerfully appearances can shape our understanding of the world around us, and how patient observation and experimentation are needed to reveal hidden truths. We see what we expect to see. Science teaches us to look deeper. Crystals form when liquids cool slowly enough for atoms to find their places. Imagine a crowded room where everyone must find their assigned seat in complete darkness, and you begin to understand why crystals need time to form properly, because each atom must drift through the surrounding liquid until it finds the location where it fits perfectly into the growing lattice. When molten rock or mineral-rich water cools too quickly, atoms freeze in place before they can arrange themselves, creating glass or other amorphous solids that lack the internal order of true crystals, their atoms jumbled in permanent disorder. But when cooling happens slowly, over decades or centuries or millions of years, atoms have time to test different positions and settle into the configuration that requires the least energy, building layer upon layer of geometric perfection. Patience is the secret ingredient. The finest crystals are those that were never rushed. The slower a crystal grows, the larger and more perfect it becomes. This relationship between time and quality explains why the most spectacular crystals formed in places where conditions remain stable for unimaginably long periods, allowing atoms to arrange themselves with precision that rapid crystallization can never achieve, each new layer settling perfectly atop the last. A crystal that forms in seconds will be tiny and flawed, riddled with defects where atoms landed in wrong places or failed to bond correctly with their neighbors, its surface dull and weak. But a crystal that grows over thousands of years develops faces as smooth as mirrors and an internal structure so perfect that light passes through without scattering, creating the clarity that makes gemstones so prized. Haste produces imperfection. Masterpieces require geological patience. Some crystals take millions of years to form deep within the Earth. In the heart of the planet, where temperatures reach thousands of degrees and pressures crush rock into fluid, the largest and most beautiful crystals are growing right now, so slowly that the change is imperceptible even across human generations, each new layer adding a thickness measured in fractions of a millimeter per century. The diamonds that find their way to jewelry shop windows began over 1 billion years ago in the depths of the Earth's mantle, where carbon atoms compressed into the hardest substance known to nature, waiting in darkness until volcanic eruptions carried them toward the surface, where humans would eventually dig them from the ground. These timescales dwarf our brief lives, reminding us that some processes in nature operate on schedules beyond our comprehension. The Earth is patient. Crystals remember time we cannot imagine. Every crystal begins as a tiny seed, a few atoms in perfect alignment. Crystal growth cannot begin from nothing, and scientists have discovered that the first step in crystallization is the formation of a microscopic nucleus, perhaps only a handful of atoms or molecules that happen to bump into each other in exactly the right orientation and stick together in the arrangement that will define the final crystal. This seed is remarkably fragile at first, and most nuclei dissolve back into the surrounding liquid before they have a chance to grow, their atoms scattering again into the chaos from which they briefly emerged. But once a nucleus reaches a critical size, it becomes stable, and additional atoms begin attaching themselves to its surface with increasing speed, drawn to the ordered structure like travelers finding shelter from a storm. From tiny seeds, great crystals grow. First comes the spark, then the structure. Crystals grow by adding new atoms to their existing structure layer by layer. Once a crystal seed exists, growth proceeds through the attachment of atoms or molecules to specific sites on its surface, building up the solid one layer at a time in a process following strict geometric rules determined by the crystal's internal structure and environmental conditions. Each new layer is a perfect copy of the one beneath, like printing the same pattern on successive sheets and stacking them together, creating a three-dimensional solid whose external shape reflects the hidden symmetry of its atomic architecture. You can sometimes see evidence of this growth in the stepped surfaces of natural crystals, where each terrace represents a period when growth paused before resuming, leaving a record of the crystal's history in stone. Growth is memory made visible. Every facet tells a story. The shape of a crystal is determined by the arrangement of its atoms. If you could shrink yourself small enough to walk through a crystal lattice, you would find yourself in a world of perfect geometric order, with atoms arranged in repeating patterns that extend in every direction like infinite three-dimensional wallpaper, and the angles between atoms dictate the angles between the faces you see on the outside. This is why salt crystals are always cubes and quartz crystals always grow with six-sided points, because the external shape is a magnified reflection of the internal atomic arrangement, scaled up billions of times from molecules to the world we can see and touch. No matter where a particular mineral crystallizes, it will develop the same characteristic angles, a property so reliable that mineralogists can identify unknown crystals simply by measuring the geometry of their faces. Atoms write the blueprint, shape is structure made visible. And from these invisible blueprints, nature builds visible wonders. There are 7 crystal systems that describe all possible crystal shapes. Despite the endless variety of crystals found in nature, from the needles of gypsum to the cubes of pyrite, every single one belongs to one of just 7 fundamental categories called crystal systems, each defined by the symmetry relationships between its axes and angles that constrain the possible shapes it can assume. These systems range from the cubic, where all 3 axes are equal and meet at right angles, to the triclinic, where no axes are equal and no angles are 90 degrees, with the other 5 systems representing intermediate degrees of symmetry. Understanding these 7 systems gives scientists a powerful tool for organizing the diversity of the mineral kingdom, reducing thousands of different minerals to a manageable framework based on underlying geometric principles. 7 patterns contain all possibilities. Infinite variety springs from limited rules. The cubic system produces crystals with perfect symmetry in all directions. In the cubic system, which scientists also call the isometric system, crystals possess the highest degree of symmetry possible in 3 dimensions, with axes of equal length meeting at right angles and faces that can be rotated and reflected in multiple ways while still looking identical to their original appearance. This elegant geometry produces crystals that appear the same from any direction. Whether you view them from above, below, or from the side, their symmetry so complete that rotating them creates no visible change. The cubic system produces some of the most famous crystal shapes in nature, including the perfect cubes of table salt, the gleaming octahedrons of diamond, and the pyridohedrons of fool's gold, each a testament to the power of atomic symmetry to create visual harmony. Maximum symmetry creates maximum beauty. Perfection has a geometry. Diamonds, salt, and gold all crystallize in the cubic system. These 3 substances, so different in their properties and value, share a common geometric heritage, atoms arranged in the same fundamental cubic pattern that produces characteristic shapes mineralogists recognize, from the cubes of halite to the octahedral faces of diamond crystals. The cubic system favors dense, efficient packing of atoms, which may explain why it produces some of the hardest and most stable substances known, materials that resist chemical attack and mechanical stress, because their atoms are locked in an arrangement without weak points. When you sprinkle salt on your food or admire a diamond in a shop window, you are looking at the visible consequences of cubic symmetry, geometry translated from the atomic scale to the human scale. Different paths lead to similar patterns. The cube unites what nature separates. The hexagonal system creates crystals with six-fold symmetry like snowflakes. In the hexagonal crystal system, atoms arrange themselves around a central axis in a pattern that repeats every 60 degrees, creating the distinctive six-sided shapes we see in quartz points, beryl prisms, and the delicate branching structures of snowflakes drifting through winter skies. This six-fold symmetry arises because the atoms bond most efficiently at angles of 120 degrees, forming hexagons that tile together perfectly like honeycomb, a pattern so stable and space-efficient that nature returns to it again and again across different chemical compositions. The hexagonal system produces some of the most beloved gemstones, including emerald, aquamarine, and purple amethyst, each displaying the characteristic six-sided prism that collectors prize, their shapes determined by the same geometric principles that guide snowflakes as they crystallize from water vapor. 6 is nature's favorite number. Hexagons tessellate into infinity. Quartz, one of the most common minerals, belongs to the hexagonal system. Quartz makes up approximately 12% of the Earth's continental crust, appearing in almost every type of rock and nearly every geological environment, from veins of gold-bearing ore to the sands of tropical beaches worn down from granite mountains. Its hexagonal crystal structure gives quartz its characteristic pointed shape, with 6 faces meeting at the tip like petals of a closed flower, a geometry so consistent that ancient peoples could recognize quartz crystals by shape alone, even before understanding anything about atoms. The abundance of quartz means that more humans have held a hexagonal crystal in their hands than any other type, whether they knew what they were holding, from clear points prized by collectors to grains of sand at the seaside. In quartz, the hexagonal becomes ubiquitous. The extraordinary hides in the ordinary. Each snowflake is a crystal of ice, unique yet following the same hexagonal rules. When water vapor freezes high in the atmosphere, ice crystals begin to form around microscopic dust particles, and from this beginning grows a structure of astonishing complexity, with branches sprouting from branches in patterns depending on temperature and humidity the snowflake encounters as it drifts through the sky. No two snowflakes follow exactly the same path through clouds, experiencing exactly the same conditions at exactly the same moments, and so no two snowflakes end up identical, each one a frozen record of its unique journey written in ice crystallography. Yet despite this infinite variety, every snowflake displays the same six-fold symmetry, because hydrogen bonds between water molecules prefer angles of 120 degrees, scaling up to the visible world in 6 arms of every snowflake. Uniqueness within unity, chaos within order. Let these ideas of symmetry and patience settle gently over you. There is no rush here. The crystals themselves took millennia to form. You have nothing to do but rest and breathe. In the spaces between atoms, the secrets of color and light are written. The color of a crystal depends on which wavelengths of light it absorbs. When white light enters a crystal, some wavelengths pass straight through, while others are absorbed by atoms within the lattice, and the color you perceive is simply the combination of wavelengths that survive this filtering process to reach your eye, a subtraction of light that creates color from what remains. A ruby appears red because chromium atoms absorb blue and green light while allowing red wavelengths to pass, and a sapphire appears blue because iron and titanium absorb red and reflect blue back toward your eye. The atoms that create these colors are usually present in tiny quantities, mere traces within an otherwise colorless crystal, and yet their effect on light is profound enough to create the vivid hues that make gemstones so prized throughout human history. Color is absence made visible. Beauty emerges from what is taken away. Impurities in a crystal can create brilliant colors from tiny amounts of foreign atoms. The most prized colors in gemstones often arise not from main elements that form the crystal structure, but from minuscule traces of other atoms that have crept into the lattice during formation, substituting for regular atoms at a rate of perhaps 1 in every 10,000 or fewer. These impurity atoms absorb different wavelengths of light than the surrounding crystal, creating splashes of color in what would otherwise be colorless stones, a chemical accident that humans have treasured for millennia without understanding the atomic mechanisms. The precise shade depends on which impurity is present, how much of it exists within the crystal, and where in the lattice foreign atoms have positioned themselves, variables so sensitive that slight differences in growing conditions can produce dramatically different colors. Perfection is colorless. It is the flaws that give us beauty. Amethyst gets its purple color from trace amounts of iron. The royal purple of amethyst, prized by kings and priests throughout history, comes from iron atoms that have substituted for silicon in the quartz structure at rates typically less than 1%, combined with exposure to natural radiation that alters the electronic state of these impurities. This irradiation changes how the iron atoms interact with light, shifting their absorption spectrum toward the blue end and creating the characteristic purple hue that varies depending on how much iron is present and how much radiation the crystal received underground. The same quartz without iron or with iron that has not been irradiated would be perfectly clear, and heating an amethyst can reverse the color change, returning the stone to transparency. Purple is an accident of chemistry. Royalty wears the fruits of chance. Rubies and sapphires are the same mineral with different impurities. This surprising fact confounds intuition, because rubies with their passionate red and sapphires with their serene blue seem completely different, yet both are corundum, a crystal of aluminum oxide forming under high pressure and temperature in metamorphic rocks. The difference between a ruby worth millions and a sapphire worth millions lies entirely in which trace elements contaminated the crystal during formation, with chromium producing the red of rubies and iron, and titanium producing blue of sapphires, while other elements create orange, pink, and yellow varieties. Pure corundum contains only aluminum and oxygen and is colorless, occasionally sold as white sapphire, demonstrating how a stone's character depends on chemical accidents of its birth. The same mother, different children. Identity is determined by accident. A ruby is red because of chromium, while sapphire is blue because of iron and titanium. Chromium atoms absorb yellow and blue-green light strongly while allowing red light to pass through. And when these atoms substitute for a few percent of the aluminum atoms in corundum, the resulting crystal glows with the distinctive red that has made rubies symbols of passion and royalty for thousands of years. Iron and titanium work together to produce the blue of sapphires through intervalence charge transfer, where electrons jump between the two different metal ions, absorbing red and orange light in the process and leaving only cool blue to reach the viewer's eye. The chemistry is straightforward once you understand it, but the beauty that emerges from these simple atomic substitutions has captivated humanity since the first ancient jeweler held a ruby up to sunlight. Atoms paint with light. We see their art without knowing their names. Pure corundum, the mineral that forms rubies and sapphires, is colorless. This transparent form of aluminum oxide, sometimes called white sapphire in the gem trade, reveals the essential truth about corundum before trace elements transform it into something precious and colorful. The crystal structure of corundum consists of aluminum atoms surrounded by oxygen atoms in a pattern so tightly packed that it creates the second hardest natural mineral, surpassed only by diamond, and this hardness makes corundum useful for industrial applications from watch crystals to sandpaper. When perfectly pure, corundum allows light to pass through unimpeded, creating a gem that sparkles with brilliance but lacks the distinctive color that makes rubies and sapphires desirable to collectors and jewelers. Ancient peoples occasionally treasured white sapphires for their clarity, not realizing they held the blank canvas upon which nature paints rubies and other sapphires. Purity is not absence, but potential. Some crystals change color depending on the angle of light. This optical phenomenon, called pleochroism, occurs because certain crystal structures absorb different wavelengths of light, depending on which direction the light travels through the atomic lattice, creating a gem that shifts color as you rotate it in your hand like a living kaleidoscope responding to your movement. Tanzanite displays this property dramatically, appearing blue when viewed from one direction and purple or bronze when viewed from another. And gem cutters must carefully orient the stone during cutting to maximize the most desirable color while minimizing less attractive tones. The physics behind pleochroism involves the anisotropic nature of certain crystal structures, where the spacing and arrangement of atoms differs along different axes, causing light polarized in different directions to interact with the crystal in fundamentally different ways. One stone contains many colors. Perspective determines what we see. Alexandrite can appear green in daylight and red under incandescent light. This remarkable chrysoberyl variety, first discovered in Russia's Ural Mountains in 1830 and named after Tsar Alexander II, exhibits color change so dramatic that collectors describe it as emerald by day and ruby by night, making it one of the most prized gemstones in existence. The phenomenon occurs because alexandrite transmits both red and green light while absorbing yellow strongly, and the balance between transmitted colors depends on the spectrum of the illuminating light source, with sunlight favoring green appearance while incandescent bulbs rich in red shift the stone toward crimson. Fine alexandrite crystals remain exceptionally rare because their formation requires the presence of both chromium and beryllium in the same geological environment, elements that rarely occur together in nature due to their different geochemical behaviors. Magic hides in rarity. Two colors share one heart. Opals contain tiny silica spheres that diffract light into rainbow colors. Unlike other gemstones that owe their colors to chemical impurities or atomic structure, opals create color through a purely physical process that depends on microscopic architecture rather than chemistry, with billions of silica spheres arranged in regular patterns that scatter light like a three-dimensional diffraction grating. When these spheres are approximately 200 to 300 nanometers in diameter and stacked in orderly rows, the opal displays brilliant flashes of color that shift and dance as the stone moves, creating the famous play of color that has enchanted humanity for thousands of years. Australian deposits produce most of the world's precious opals, formed when silica-rich water percolated through ancient sandstones and gradually deposited layer upon delicate layer of microscopic spheres over millions of years. The rainbow trapped in stone, light becomes its own decoration. The play of color in opals shifts and dances as you turn the stone. This mesmerizing movement of color patches across the surface of a precious opal results from viewing different regions of the silica sphere array as the angle between eye, stone, and light source changes, with each tiny domain of stacked spheres diffracting a specific color that appears and disappears as your perspective shifts. The phenomenon captivated ancient Romans who valued opals above all other gems, believing the stone contained the combined beauty of all precious stones in one magical package, while Australian Aboriginal legends described opals as rainbow fragments that fell to earth. Different regions of an opal may contain spheres of different sizes, creating patches that flash different colors, and the most valuable opals display a full spectrum of hues dancing across their surface in patterns that never repeat. Motion creates meaning. Stillness hides the rainbow within. Deep beneath the surface, in caverns we may never see, crystals grow to astonishing sizes. The Cave of Crystals in Mexico contains gypsum crystals over 10 meters long. Discovered accidentally in 2000 by miners drilling for lead and silver in the Naka mine in Chihuahua, this underground chamber holds the largest natural crystals ever found, transparent selenite beams that dwarf humans and create an environment so alien it resembles science fiction more than anything terrestrial. The crystals grew to these dimensions because the cave remained submerged in mineral-rich water at nearly constant temperature just below the saturation point for gypsum for approximately 500,000 years, allowing molecules to add themselves to existing crystal surfaces at imperceptibly slow rate that accumulated into structures weighing many tons. These crystal beams cross the chamber at various angles, creating a geometric maze that visitors must navigate carefully to avoid damaging formations that took 500,000 years to create. Giants grow in patience. Time builds cathedrals. These giant crystals grew in water heated by volcanic activity for 500,000 years. A magma chamber beneath the Naka mountain provides the heat source that maintained the cave at approximately 58 degrees Celsius for geological ages, warming mineral-rich groundwater and creating conditions so stable that gypsum crystals could grow continuously without interruption for longer than humans have existed as a species. The water remained saturated with calcium sulfate at this precise temperature, sitting just below the point where gypsum would dissolve and just above where rapid crystallization would produce many small crystals instead of few large ones. When mining operations pumped out the water to access ore deposits, the crystals were exposed to air for the first time, immediately beginning to deteriorate from humidity changes and temperature fluctuations. The recipe required perfection. We arrived just in time to see it. The cave is so hot that humans can only survive inside for a few minutes. At 58 degrees Celsius, with nearly 100% humidity, the Cave of Crystals presents conditions so extreme that the human body cannot cool itself through sweating because saturated air prevents evaporation, causing core temperature to rise dangerously within minutes, even with ice-cooled suits. Scientists exploring the cave carry backpacks filled with ice and wear suits cooled by chilled air, limiting their visits to 20 or 30 minutes before they must retreat to cooler tunnels beyond the chamber to prevent hypothermia. The same conditions that allowed crystals to grow for 500,000 years make the cave hostile to complex life, and researchers found only specialized bacteria living in fluid inclusions within the crystals, organisms sealed inside for tens of thousands of years. Beauty demands sacrifice. The greatest treasures resist our grasp. Giant crystal caves exist because conditions remained stable for geological ages. The fundamental requirement for growing crystals of extraordinary size is time combined with unchanging conditions, because any fluctuation in temperature, pressure, or chemistry that causes crystals to partially dissolve resets the growth process, while stability allows continuous accumulation that can proceed for millions of years. Most crystallization environments on Earth experience constant change from seasonal variations, tectonic movement, and groundwater fluctuations that interrupt crystal growth before giant specimens can form, making caves like Naka exceptional products of geological coincidence, where volcanic heat, isolated chambers, and stable chemistry persisted unchanged. Similar giant crystal caves may exist elsewhere on Earth, still hidden and undiscovered, waiting in the darkness with crystal guardians standing silent watch over chambers no human eye has ever seen. Patience produces monuments. Time is the ultimate sculptor. Some geodes are hollow rocks lined with crystals that sparkle like secret treasure chambers. These spherical or oblong rock formations develop when gas bubbles become trapped in volcanic lava, or when organic material decays within sedimentary deposits, leaving hollow cavities that gradually fill with mineral-rich water, depositing layer upon layer of crystals on the inner walls over thousands or millions of years. The exterior of a geode typically appears as an unremarkable rounded stone, gray or brown and rough, giving no indication of the crystalline wonderland hidden within until someone cracks it open to reveal sparkling quartz points, purple amethyst clusters, or other mineral treasures. Children and adults alike experience a particular joy when opening geodes, because the anticipation of not knowing what lies within combines with the revelation of beauty hidden beneath ordinary surfaces. Secrets hide in plain sight. Every stone might be a universe. Geodes form when mineral-rich water seeps into hollow spaces in rock. The process begins when volcanic or sedimentary processes create a cavity, perhaps from a gas bubble in cooling lava or from an animal burrow that decayed, and groundwater carrying dissolved minerals slowly infiltrates this hollow space and deposits thin layers of silica or calcite on the inner surface with each evaporation cycle. Over thousands to millions of years, these layers build inward from the cavity walls, sometimes completely filling the space, but more often leaving a hollow center lined with crystal points that grow freely into the open void, where they can develop their natural geometric faces. The specific minerals in the groundwater determine what crystals form inside the geode, with silica-rich water producing quartz and amethyst, while calcium-rich water might fill the cavity with calcite crystals. Water writes in stone. Patience fills the void with wonder. You cannot tell a geode from an ordinary rock until you crack it open. This element of surprise makes geode hunting a popular hobby, because the dull exterior of these rounded stones reveals nothing about the potential treasures within, and two geodes sitting side by side might contain vastly different formations, ranging from disappointing muddy quartz to spectacular amethyst cathedrals worth thousands. Experienced collectors look for round or egg-shaped rocks that feel lighter than expected for their size, indicating a hollow interior. But even experts admit that the only certain way to know what lies within is to break the geode open by scoring a line around the equator and tapping carefully. The moment of revelation never loses its excitement, whether you are a professional gem dealer opening your 1000th geode or a child cracking your first stone to discover the sparkle hidden inside. Anticipation tastes sweeter than certainty. Mystery wraps every treasure. The largest amethyst geode ever found weighs over 2 tons. Named the Empress of Uruguay and standing over 3 meters tall, this spectacular specimen was discovered in the Artigas region of northern Uruguay. an area famous for producing large geodes in ancient lava flows that created ideal conditions for crystal formation approximately 130 million years ago. The interior of this massive geode blazes with deep purple amethyst crystals of exceptional color and clarity, and the specimen now resides in a crystal cave museum in Australia, where visitors can walk inside a room built to house this and other giant geodes. Finding such large specimens requires both luck and expertise, because the geode must survive geological processes that would crush ordinary cavities, and someone must recognize the exterior rock as potentially containing something extraordinary within. Giants hide in ordinary disguises. Size does not announce itself. Crystal caves are fragile ecosystems that can be destroyed by a single careless touch. The same conditions that allow crystals to grow undisturbed for thousands of years make these formations incredibly vulnerable to human contact. Because the oils and acids on human skin can etch crystal surfaces, body heat can cause microscopic fractures in temperature-sensitive minerals, and even a careful touch can snap formations that appear solid. Many crystal caves have been damaged or destroyed by visitors who removed specimens as souvenirs before the sites became protected, and even well-intentioned expeditions must balance the desire for knowledge against the risk of destroying formations that took longer to create than human civilization has existed. Conservation efforts now seal some caves entirely, allowing only occasional visits under strict protocols, while others install walkways that keep visitors at safe distance from delicate formations. We must learn to love without touching. Some beauty requires only our eyes. And among these natural wonders, some crystals have become treasures beyond measure. Diamonds are crystals of pure carbon formed under extreme pressure. In the upper mantle of the Earth, approximately 150 to 200 kilometers beneath our feet, temperatures exceed 1,000 degrees Celsius and pressures reach 50,000 times atmospheric. And under these conditions, carbon atoms bond together in a tetrahedral arrangement, where each carbon shares electrons with 4 neighbors in a pattern so strong the crystal resists scratching by any other natural material. The same carbon atoms that form soft graphite in your pencil become the hardest natural substance when squeezed and heated beyond anything we experience in daily life, demonstrating how the same element can manifest different properties depending on atomic arrangement. This process requires not only extreme conditions, but also time, with most natural diamonds having formed between 1 and 3 billion years ago. Pressure creates perfection. Fire and time forge immortality. Most diamonds formed over 1 billion years ago, more than 100 kilometers below the surface. These ancient crystals predate not only humanity, but also most complex life on Earth, having crystallized in the deep mantle during the Archean and Proterozoic eons, when our planet was young and the atmosphere was unbreathable, making diamonds some of the oldest objects you could hold in your hand, aside from meteorites. Some diamonds contain tiny inclusions of other minerals trapped during formation that provide scientists with samples of the deep Earth from eras when the mantle chemistry differed from today, creating time capsules from epochs we could never otherwise access. The age of diamonds contributes to their symbolic association with eternity and enduring love, because these crystals have persisted through almost the entire history of our solar system, unchanged in the darkness beneath ancient continents. Old before life began, witnesses to the childhood of Earth. Diamonds reach the surface through violent volcanic eruptions called kimberlite pipes. Named after the South African town of Kimberley, where such a pipe produced famous diamond mines in the 19th century, These volcanic conduits represent some of the deepest and most explosive volcanic events on Earth, rocketing magma from depths of over 200 kilometers to the surface at speeds approaching 2,000 kilometers per hour, fast enough that diamonds do not have time to convert back into graphite. The kimberlite magma contains fragments of the mantle it passed through on its rapid journey upward, creating a geological sample of deep Earth, and diamonds are simply the most glamorous components of this deep Earth debris. Most kimberlite pipes are ancient, having erupted millions of years ago, and finding new diamond-bearing pipes requires sophisticated prospecting because surface expressions erode away over time. Speed preserves treasures. The journey up must be violent. The hardest natural substance on Earth is diamond. Hardness in mineralogy refers specifically to resistance to scratching rather than resistance to breaking. And on the Mohs scale, where talc is 1 and corundum is 9, diamond sits alone at 10, so far above the next hardest mineral that the gap between 9 and 10 is greater than all other gaps combined. This extreme hardness results from the strong covalent bonds between carbon atoms arranged in the tetrahedral diamond lattice, where each atom is held firmly in place by 4 equal bonds that must all be broken simultaneously for the crystal to yield, creating a structure without weak points. Industrial applications consume most mined diamonds because nothing else cuts and polishes hard materials as effectively, with diamond saw blades and drill bits serving essential roles in construction and manufacturing. Strength lies in structure. Every bond pulls its weight. Diamond can only be scratched by another diamond. This principle has profound practical implications for gem cutting and polishing, because the only way to shape a diamond into the brilliant faceted gems we admire is to grind it against other diamonds, using diamond powder suspended in oil to gradually wear away material in a process that can take days or weeks for a single large stone. Before modern polishing techniques developed in the 15th century, diamonds were often worn in their natural crystal form because craftspeople had not yet mastered cutting the hardest substance on Earth, and the brilliant cuts we associate with diamonds today represent centuries of accumulated knowledge about manipulating light using precise faceting. Each facet is polished to mirror smoothness using progressively finer diamond powder, a process where the hardest substance becomes both tool and material. Identity defines limits. Only equals can shape equals. The Hope diamond is famous for its deep blue color and its legendary curse. Weighing over 45 carats and displaying a rare blue color caused by trace boron in its structure, the Hope diamond has passed through multiple royal collections and private hands since its origin in India more than 3 centuries ago, accumulating stories of misfortune that befell its owners. The alleged curse provided excellent publicity and helped establish it as one of the most recognized gems in the world, now residing in the Smithsonian National Museum of Natural History, where millions view it each year, though historians have debunked many of the deaths as exaggerations or coincidences. Beyond its legendary status, the Hope diamond contributes to science because recent studies of its phosphorescence revealed unique properties that help geologists understand how blue diamonds form and from what depths they originate. Stories enhance value. Mystery adorns the measurable. Allow yourself to drift with these images of buried treasure and ancient depths. Your breath can slow now, deep and steady, like the patient growth of crystals in the dark. Emeralds are crystals of beryl-colored green, bichromia and vanadium. The beryl mineral family includes several beautiful gemstones, including aquamarine and morganite, but emerald stands apart as the most valuable member, prized since ancient times for its vivid green color that symbolizes spring, renewal, and the living world in cultures across the globe. Chromium is the primary coloring agent, substituting for aluminum atoms in the beryl crystal structure and absorbing light in the red and blue portions of the spectrum while transmitting green. And vanadium sometimes contributes additional green tones depending on the geological conditions. The finest emeralds display a pure green color with high saturation and medium tone, neither too light nor too dark, and the specific shade varies by origin, with Colombian emeralds showing warmer tones, while Zambian stones tend toward cooler blue-green hues. Green light captured in stone. Nature bottles the color of life. Cleopatra was famous for her love of emeralds from Egyptian mines. The last pharaoh of Egypt adorned herself with emeralds from mines that bore her name near the Red Sea coast, gems extracted from pegmatite veins in the eastern desert since at least 1500 BCE and continuing through Roman times before eventually being abandoned and lost to the shifting sands. Cleopatra reportedly gave emerald jewelry to visiting dignitaries, and the Romans who conquered Egypt continued mining operations, prizing these green stones for their association with fertility and rebirth, though the quality of Egyptian emeralds rarely matched specimens later discovered in Colombia. Archaeological investigations have rediscovered these ancient mines, finding tools, workers' huts, and small emerald crystals still embedded in quartz veins that miners overlooked or deemed too difficult to extract. Queens and stones share names, both endure beyond their kingdoms. Most emeralds contain tiny fractures called jardin, meaning garden in French. Unlike diamonds, where clarity is paramount and inclusions are considered flaws, emeralds commonly contain networks of tiny fractures, fluid inclusions, and mineral traces that gemologists poetically call jardin because they resemble the tangled vegetation of a garden when viewed under magnification. And these characteristics are so ubiquitous that an emerald without jardin raises suspicion of being synthetic. The fractures form because emerald crystals grow in geological environments characterized by tectonic stress, hydrothermal activity, and temperature fluctuations that leave the growing crystal full of tiny imperfections that paradoxically help authenticate it as natural rather than laboratory created. Dealers and collectors learn to appreciate certain types of jardin that indicate prestigious origins, with Colombian three-phase inclusions containing liquid, gas, and solid salt crystals being particularly distinctive and valuable as proof of origin. Flaws become fingerprints. Imperfection authenticates beauty. Rubies were once considered more valuable than diamonds. Before the great diamond discoveries in South Africa during the late 19th century, rubies commanded the highest prices of any gemstone, with ancient Sanskrit texts referring to rubies as Ratnaraj, meaning king of precious stones, and Marco Polo reportedly described the king of Ceylon as possessing a ruby he refused to sell for an entire city's value. The rarity of fine rubies exceeding 5 carats has always been extreme, far exceeding diamonds of similar size, and even today a flawless ruby of top color commands prices per carat higher than an equivalent diamond, with exceptional stones selling for over £1 million per carat. Diamond marketing in the 20th century shifted cultural preferences, but connoisseurs continue to value exceptional rubies as among the rarest of all gems. Value is fashion. Rarity changes perception over centuries. The finest rubies come from Myanmar and are called pigeon blood rubies. This evocative name describes a very specific shade of red, intensely saturated with a slight bluish undertone and a strong fluorescence that makes the stone appear to glow from within, a color historically associated with the Magok Valley in Myanmar, where exceptional rubies have been mined for centuries. The term pigeon blood originally referred to the color of a freshly killed pigeon's blood, dark and pure. And while modern gemological laboratories have attempted to standardize the definition, the traditional name persists in the trade as shorthand for rubies of the finest color, regardless of geographic origin. Rubies from other sources, including Thailand, Madagascar, and Mozambique, can approach this ideal color under certain conditions, but Burmese stones from Magok remain the standard against which all others are measured. Names carry history. The perfect color has a geographic home. Beyond their beauty, crystals possess remarkable physical properties. Some crystals can generate electricity when squeezed. This remarkable property means that mechanical pressure applied to certain crystalline materials produces an electric voltage across the crystal faces, and conversely, applying voltage causes the crystal to physically deform, creating a two-way relationship between mechanical and electrical energy that engineers have exploited for over a century in applications ranging from cigarette lighters to precision instruments. The phenomenon occurs because the crystal structure lacks a center of symmetry, meaning that compressing the crystal shifts positive and negative charges differently from each other, creating a net separation of charge that manifests as measurable voltage. Not all crystals display this property since it requires specific asymmetric atomic arrangements, but those that do have transformed modern technology in ways most people never notice despite using piezoelectric devices daily. Pressure speaks in voltage. Crystals translate force to electricity. This property is called piezoelectricity, from the Greek word for pressure. Pierre and Jacques Curie discovered piezoelectricity in 1880 while studying quartz and tourmaline crystals, demonstrating that pressure applied along certain directions produced measurable electrical charges on the crystal surfaces, a finding that remained a scientific curiosity before practical applications emerged. The Greek root piezo means to squeeze or press, perfectly describing the physical action that generates the electrical response, and the Curie's systematic study established the theoretical foundation that later engineers would use to develop practical piezoelectric devices during and after the First World War. Today, piezoelectricity appears in countless applications, from spark generation in gas lighters to the scanning tips in atomic force microscopes that can image individual atoms, demonstrating how a basic physics discovery can evolve into technologies its discoverers could never have imagined. Greek names preserve discoveries. The language of pressure became the language of precision. Quartz watches keep time using the piezoelectric vibration of a tiny crystal. Inside every quartz watch sits a small tuning fork made from crystalline quartz, typically a few millimeters long, that vibrates at a precise frequency when electricity passes through it, and an electronic circuit counts these vibrations to measure time with accuracy far exceeding mechanical watches. The piezoelectric effect works both ways in this application. The initial electrical pulse causes the quartz to vibrate, and this vibration generates return electrical signals that the circuit detects and counts, creating a feedback loop that maintains oscillation indefinitely as long as power remains available. Before quartz technology became affordable in the 1970s, mechanical watches represented the pinnacle of timekeeping for portable devices, but the superior accuracy and lower cost of quartz movements rapidly displaced mechanical watches in all but luxury and collector markets. Crystals count time. Vibration measures existence. A quartz crystal vibrates exactly 32,768 times per second. This oddly specific number is actually a power of 2, specifically 2 to the 15th power, chosen because electronic circuits that divide frequencies work efficiently with powers of 2, making it simple to count down from 32,768 vibrations to 1 pulse per second using 15 binary divisions. The actual vibration frequency depends on the crystal's physical dimensions and cut, so watchmakers shape quartz crystals with extreme precision to achieve this target frequency, knowing that any deviation will cause the watch to run fast or slow over time. Temperature affects vibration rate slightly, and better quartz watches include temperature compensation circuits or use specially cut crystals that minimize thermal drift, achieving accuracy of a few seconds per month compared to hours of drift for mechanical watches. Math determines music, powers of 2 mark seconds. Piezoelectric crystals are used in microphones, speakers, and medical ultrasound. The same physical principle that powers quartz watches enables a range of technologies that convert between sound and electricity, with piezoelectric elements serving as the sensitive heart of many devices we use without ever considering the crystalline structure that makes them function. In microphones, sound waves compress a piezoelectric element that generates corresponding electrical signals, while in speakers, the process reverses with electrical signals, causing piezoelectric materials to vibrate. And in medical ultrasound, both processes combine as transducers emit high-frequency sound pulses, then detect echoes bouncing back from internal organs. The versatility of piezoelectricity extends far beyond these applications to include sonar systems that map the ocean floor, fuel injectors in diesel engines, and the tiny motors that focus smartphone cameras. One principle serves many masters. Crystals speak and listen in every device. Some crystals can bend light in 2 directions at once. This bizarre optical property occurs because certain crystal structures have different refractive indices along different crystallographic axes, meaning that a single ray of light entering the crystal splits into 2 rays that travel at different speeds and slightly different directions, each carrying half of the original intensity. The effect is immediately visible when you place a birefringent crystal over printed text, because each letter appears twice, offset by the distance between the 2 light paths inside the crystal, creating an unsettling doubling effect that violates ordinary optical experience. The physics involves the anisotropic electric polarizability of the crystal structure, where electrons respond differently to electric fields oscillating in different directions, and this asymmetry causes the crystal to present different optical properties depending on polarization of incoming light. Light learns 2 paths. Crystals teach division. This phenomenon is called double refraction or birefringence. The term birefringence combines Latin roots meaning twice and breaking, accurately describing how the crystal breaks a single light beam into 2 distinct rays, while double refraction refers to the same phenomenon from the perspective of the 2 different refractive indices that the crystal presents to different polarizations of light. Erasmus Bartholinus first described birefringence scientifically in 1669 after observing the double image effect in calcite crystals from Iceland, and Christian Huygens later used this observation to develop his wave theory of light. demonstrating how a property of crystals could illuminate fundamental physics. Modern scientists measure birefringence precisely because it provides information about crystal structure, stress in materials, and the properties of biological tissues, with polarized light microscopy revealing details invisible to ordinary illumination. Breaking light reveals structure. Two paths tell twice the story. Calcite crystals make words appear doubled when you look through them. Transparent calcite, sometimes called Iceland spar because historically fine specimens came from Iceland, provides such strong birefringence that the doubling effect is immediately obvious without any magnification, making it the standard demonstration material for this optical phenomenon in classrooms and museums. The two images form because light polarized parallel to the crystal axis follows a different path than light polarized perpendicular to it, with the difference in refractive index being substantial enough that the two rays emerge separated by a visible distance that increases with crystal thickness. Medieval scholars sometimes used calcite crystals to read difficult manuscripts by shifting the doubled image until the two copies merged more clearly, and jewelers employ the same property to test gemstones because minerals with high birefringence show doubled back facets. Transparency multiplies. Clear stones teach optical physics. Vikings may have used calcite crystals to navigate by finding the sun on cloudy days. Medieval Norse sagas mention mysterious sunstones that allowed seafarers to locate the sun even when clouds obscured the sky, and researchers have demonstrated that calcite crystals can indeed accomplish this by revealing the polarization pattern of skylight that persists even when the sun itself is invisible. The technique involves rotating the crystal while looking at a patch of sky and observing when the two images appear equally bright, which occurs when the crystal's optical axis aligns with the direction of maximum polarization, pointing toward the hidden sun. Experimental tests showed that skilled observers can determine the sun's position to within a few degrees using this method, potentially explaining how Viking navigators crossed the North Atlantic with remarkable precision centuries before the magnetic compass reached northern Europe. Ancient sailors read the sky. Crystals pointed the way home. And in the modern world, crystals have become essential to our technology. Silicon crystals are the foundation of nearly all modern electronics. Every smartphone, laptop, server, and digital device depends on the semiconducting properties of crystalline silicon to process information. By controlling the flow of electrons through circuits containing billions of transistors etched into the crystal surface, using photolithography techniques that have improved continuously for over 60 years. Silicon occupies a unique position in the periodic table, where its electrical conductivity falls between metals and insulators, allowing engineers to precisely control current flow by adding tiny amounts of other elements to different regions of the crystal, creating the junctions and channels that form transistors and other electronic components. The silicon revolution began in the 1950s and has followed an exponential growth curve that doubled computing power roughly every 2 years, transforming human civilization more rapidly than any technology since fire. Sand becomes thought. Crystals compute consciousness. Computer chips are carved from single crystals of ultra-pure silicon. Manufacturing computer chips requires starting with a single crystal of silicon, not a collection of many small crystals stuck together, because grain boundaries between separate crystals would disrupt electron flow and ruin the electrical properties that transistors require. So the semiconductor industry grows massive single crystals called ingots. The Czarkowski process accomplishes this by dipping a tiny seed crystal into a crucible of molten silicon and slowly withdrawing it while rotating, allowing atoms from the melt to add themselves to the seed in perfect crystallographic alignment, building up a continuous single crystal over many hours. These ingots are then sliced into thin wafers that undergo hundreds of processing steps to create the circuit patterns of computer chips, with each wafer potentially yielding hundreds of chips worth thousands of pounds. One seed grows an industry, perfection birthed in fire. The silicon crystals used in electronics must be 99.999999% pure. This extreme purity requirement, often described as 9 nines pure, means that fewer than 1 in a billion silicon atoms can be something other than silicon, because even tiny contamination levels would interfere with the precise doping that creates transistors and other circuit elements. Achieving this purity requires multiple steps of refining and purification, including zone refining, where a molten zone passes through a solid ingot, and impurities preferentially dissolve in the liquid, gradually sweeping contaminants toward one end that is then discarded. The resulting ultrapure silicon is then intentionally contaminated in precisely controlled ways, adding specific dopant atoms to specific locations to create the semiconductor junctions that make transistors work, where the purity requirement ensures that only the intended dopants affect the crystal's electrical properties. Perfect purity enables perfect control. Electronics demand atomic precision. Liquid crystal displays use crystals that change orientation in response to electricity. Liquid crystals occupy a fascinating state of matter between solid and liquid, where elongated molecules maintain orientational order like crystals but can flow like liquids, and this combination allows electric fields to change how the molecules align, which changes how light passes through them. Display screens exploit this property by sandwiching liquid crystal material between glass plates with transparent electrodes and polarizing filters arranged so that light passes through when the crystals are in one orientation, but is blocked when an electric field rotates them. Each pixel on a liquid crystal display contains 3 subpixels with colored filters and independent electrodes, and by controlling the voltage at each subpixel, the display can create millions of colors at each location, assembling images from arrangements of red, green, and blue dots. Crystals paint with voltage. Molecules dance to electric commands. The screen you watch every day is filled with millions of tiny crystals twisting in unison. Consider the extraordinary coordination required for a modern high-definition display, where over 8 million pixels containing more than 24 million liquid crystal subpixels must all respond correctly and simultaneously to create smooth video at 60 frames per second, executing precise movements in perfect synchronization with their electronic commands. The liquid crystal molecules in each subpixel rotate by amounts proportional to the applied voltage, modulating the light from the backlight in a continuous range of intensities rather than simply on or off. And this analog control enables the smooth gradients and subtle shadows that make digital images appear realistic. When you watch a film or scroll through photographs, you are witnessing a choreographed performance by trillions of molecules, all following electrical instructions to paint pictures with polarized light. A dance performed in silence. Every image is a crystal ballet. Ruby crystals were used in the first laser ever built. Theodore Maiman constructed the first working laser in 1960 using a synthetic ruby rod as the gain medium, demonstrating that the chromium atoms embedded in the crystal could be stimulated to emit coherent light when pumped with energy from a flash lamp wrapped around the ruby cylinder. The ruby laser emitted brief pulses of intense red light at 694 nanometers, the wavelength corresponding to the electronic transition in chromium that gives rubies their color. And this first demonstration sparked a revolution in physics, engineering, and technology that continues today. Ruby lasers remain useful for applications including tattoo removal, holography, and industrial processes, though many other laser types using different crystals, gases, and semiconductors have been developed for applications from surgery to telecommunications. Old gems birth new light. The first laser spoke ruby red. Lasers work by stimulating atoms in a crystal to release light in perfect synchronization. The word laser abbreviates light amplification by stimulated emission of radiation, describing a process where excited atoms release photons that match incoming photons exactly in wavelength, phase, and direction, creating an avalanche of identical light waves that emerge as a coherent beam, unlike anything produced by ordinary sources. In a crystal laser, the host material contains atoms of a different element, like chromium in ruby, that absorb pump light and emit it at a different wavelength when stimulated, with the crystal structure holding these active atoms in precise positions. The mirrors at each end of the laser cavity bounce light back and forth through the crystal thousands of times, with each pass amplifying the beam until enough intensity builds to escape through the output mirror. Crystals amplify coherence. Light learns to march in step. Fiber optic cables use glass that has been purified to crystalline perfection. Modern optical fibers transmit light for hundreds of kilometers without amplification, a feat requiring glass purer than the purest natural crystals, with impurity levels measured in parts per billion that would have seemed impossibly low to glassmakers of previous centuries. The silica glass in optical fibers approaches crystalline perfection in its molecular structure, even though it technically remains amorphous, meaning its atoms lack the long-range periodic order of true crystals, but maintain the short-range order and transparency that allow light signals to travel long distances. Telecommunication networks depend on these glass threads thinner than human hair, carrying pulses of laser light that encode millions of telephone calls, video streams, and internet connections simultaneously through each strand, making modern digital communication possible. Purity carries information. Glass threads bind the world. Scientists can now grow synthetic crystals that rival natural ones in quality. Laboratory crystal growth began in earnest during the 19th century and has advanced to the point where synthetic rubies, sapphires, emeralds, and diamonds can be produced that are chemically and physically identical to their natural counterparts, distinguishable only by subtle characteristics that require specialized equipment to detect. The ability to control temperature, pressure, and chemistry precisely allows crystal growers to avoid the inclusions and imperfections that natural crystals acquire during their chaotic formation in the earth, potentially producing synthetic stones that exceed natural specimens in clarity and optical perfection. Industrial applications consume most synthetic crystals, but gem-quality synthetic stones also enter the jewelry market at prices significantly below natural equivalents, raising complex questions about authenticity, value, and the meaning of rarity that the gem trade continues to navigate. Laboratories imitate geology. Human patience now rivals time. Synthetic diamonds are now used in cutting tools, surgery, and electronics. The ability to manufacture diamonds in laboratories has transformed multiple industries that depend on the extreme hardness, thermal conductivity, and optical properties of crystalline carbon, making available quantities and forms of diamond that could never be economically sourced from natural deposits. Cutting tools tipped with synthetic diamond saw through concrete, granite, and other hard materials with speeds and precision impossible before industrial diamond became affordable, while surgical scalpels made from single crystal diamond maintain atomic-level sharpness that produces cleaner incisions and potentially faster healing than steel blades can achieve. Electronics applications are expanding rapidly as engineers discover that diamond's thermal conductivity, electrical properties, and resistance to radiation make it potentially superior to silicon for certain advanced applications, though manufacturing challenges currently limit widespread adoption. Created carbon serves creation. Pressure replicated brings progress. Life itself has learned to build with crystals over billions of years. Your bones contain tiny crystals of calcium phosphate. The structural strength of bone comes from a composite architecture combining flexible collagen protein fibers with rigid hydroxyapatite crystals only nanometers in size, distributed throughout the collagen matrix like reinforcing bars in concrete, creating a material stronger, pound for pound, than steel, yet capable of repair throughout your lifetime. These microscopic crystals grow within and around the collagen fibrils as bone develops, oriented along the directions of mechanical stress to provide maximum strength where needed, and specialized cells continuously dissolve and reform these crystals in response to changing loads and calcium demands. The mineral component of bone serves as your body's calcium bank, releasing calcium into the bloodstream when dietary intake falls short and depositing it back when supply exceeds demand, making your skeleton an active participant in maintaining chemical balance. You are part mineral. Crystals hold you upright. As you rest, imagine your own skeleton, quietly crystalline, holding you gently in place. Let your muscles soften around those patient mineral structures. You are partly made of stone. Tooth enamel is the hardest substance in the human body, and it is crystalline. The outer layer of your teeth consists almost entirely of hydroxyapatite crystals arranged in long, tightly packed rods that extend from the inner dentin to the outer surface, creating a mineral barrier harder than most steels that can withstand decades of chewing and exposure to acids and bacteria. Unlike bone, enamel contains no living cells and cannot repair itself once damaged, making it a one-time crystalline gift that must last the lifetime of the tooth, which explains why dental care focuses on preservation rather than treatment. The hardness of enamel allows teeth to cut through tough foods and resist the constant mechanical stress of chewing millions of times, while its mineral composition makes it vulnerable primarily to acid attack that dissolves the crystalline structure one molecule at a time. Permanent crystals armor your smile. Hard lessons in crystalline defense. Kidney stones are painful crystals that form inside the body. When urine becomes supersaturated with minerals like calcium oxalate, uric acid, or struvite, crystals nucleate and grow in the kidney, sometimes remaining small enough to pass unnoticed, but sometimes growing large enough to cause excruciating pain as they travel down the narrow ureter toward the bladder. The same crystallization chemistry that produces beautiful geodes and sparkling gemstones operates inside the human body when conditions favor mineral precipitation over dissolution, creating stones that can grow to several centimeters in diameter if not detected and treated. Prevention strategies focus on altering urine chemistry through diet and hydration to keep mineral concentrations below the saturation point where crystallization begins, essentially applying knowledge of crystal growth learned from geological and industrial contexts to the biological challenge of keeping mineral accumulation under control. Beauty has a painful twin. Crystals grow where they can. The inner ear uses tiny crystals called otoliths to sense gravity and balance. Deep within each ear, small organs called the utricle and saccule contain beds of hair cells topped with a gelatinous membrane, embedded with thousands of calcium carbonate crystals that shift position as your head tilts, bending the hair cells to signal your brain about orientation relative to gravity and linear acceleration. These microscopic crystals, each roughly 3 to 5 micrometers across, provide the necessary density difference that allows the membrane to respond differently from surrounding fluid when the head moves, creating a biological accelerometer sensitive enough to detect tilts of less than 1 degree. The vestibular system, combining these crystal-based gravity sensors with fluid-filled semicircular canals that detect rotation, gives you the unconscious sense of spatial orientation that keeps you balanced while walking, running, and sleeping. Crystals keep you upright. Gravity speaks through stones. When otolith crystals become dislodged, you can experience vertigo. Benign paroxysmal positional vertigo occurs when otolith crystals break free from the utricle and migrate into the semicircular canals where they do not belong, confusing the balance system with false signals of rotation that cause intense dizziness triggered by certain head movements. The displaced crystals settle in the canal fluid and shift when you turn your head, stimulating hair cells that normally respond only to fluid flow during actual rotation, sending signals to the brain that conflict with visual input and other sensory information about body position. Treatment often involves a series of specific head movements designed to guide the loose crystals out of the semicircular canal and back toward the utricle where they can reattach or dissolve, demonstrating how understanding crystal physics can contribute to medical practice. Misplaced stones spin the world. Position matters in crystalline balance. Shellfish build their shells from crystalline calcium carbonate. Mollusks, corals, and many other marine organisms construct protective shells and skeletons from calcium carbonate crystals that they precipitate from seawater using specialized cells and organic scaffolds, guiding crystal growth into intricate architectures far more complex than anything formed by purely geological processes. The two main crystal forms of calcium carbonate used by marine life are calcite and aragonite, each with different properties that organisms exploit for different purposes, with nacre using aragonite tablets, while many coral skeletons use calcite with its greater stability under changing conditions. Ocean acidification caused by increased carbon dioxide absorption threatens these organisms by reducing calcium carbonate saturation in seawater, making it harder to precipitate crystals and potentially dissolving existing shells in the most acidified waters. Life learned to build in stone. Crystals form the armor of the sea. Pearls are formed when mollusks coat irritants with layers of crystalline nacre. When a grain of sand, parasite, or other irritant lodges inside an oyster or mussel, the mollusk responds by secreting nacre, the same iridescent material that lines the inner shell, layer upon layer around the intruder, until a pearl emerges over months or years of crystalline deposition. Each layer of nacre consists of microscopic aragonite tablets roughly half a micrometer thick, stacked like bricks with thin organic layers between them, creating a composite that combines the hardness of crystalline calcium carbonate with the toughness of organic polymers more effectively than either component alone. Natural pearls large enough for jewelry are extraordinarily rare because most irritants are expelled before nacre accumulation begins, while cultured pearls are produced by introducing a bead nucleus and allowing it to be coated over several years. Irritation transforms to beauty. Defense becomes adornment. The iridescence of pearls comes from light diffracting through crystalline layers. The characteristic shimmer and color play of fine pearls results from the interaction of light with the layered microstructure of nacre, where aragonite tablets roughly the same size as visible light wavelengths create diffraction and interference, effects that separate white light into component colors. When light enters the pearl surface, some reflects from outermost layers, while some penetrates deeper and reflects from subsequent layers. And when these rays recombine, they interfere constructively at certain wavelengths determined by layer thickness, creating colors that seem to glow from within. The quality of a pearl's luster depends on how uniformly and tightly packed its nacre layers are, with finer, more regular layering producing more intense iridescence, which is why the best pearls seem almost to emit light rather than merely reflect it. Layers paint with light. Structure creates the glow. Sea urchin spines are single crystals that direct light to photoreceptors. Despite having no eyes in the conventional sense, certain sea urchins respond to visual stimuli using their entire body surface as a compound eye, with calcite spines apparently functioning as crude lenses that focus light onto photoreceptor cells scattered across the skin beneath. The surprise extends to the spines themselves, which, despite their complex branching shapes, are each composed of a single crystal of calcite rather than many small crystals fused together, demonstrating biological control over crystal growth that produces structures impossible by purely geological means. The optical properties of calcite, combined with the precise geometry of the spines, may allow sea urchins to detect shadows and movement well enough to avoid predators or seek shelter, though the exact mechanism remains a subject of active research. Living lenses watch without eyes. Single crystals became sentinels. Some bacteria create magnetic crystals to navigate using the Earth's magnetic field. Magnetotactic bacteria produce chains of magnetite crystals, each roughly 50 nanometers across and magnetically single-domain, aligned along the length of the cell like a biological compass needle that orients the bacterium along magnetic field lines without any active sensing or decision-making required. These microscopic organisms use magnetism to distinguish up from down in the water column, helping them find the optimal oxygen concentration for their metabolism in sediments where gradients are otherwise difficult to detect, essentially outsourcing navigation to physics encoded in crystalline chains. The precision of bacterial magnetite crystals has attracted attention from materials scientists who study how organisms control mineral formation at the nanoscale, and the distinctive crystal shapes even serve as potential biosignatures in the search for ancient life in Martian rocks. Crystals become compass needles. Bacteria navigate by magnetism. Throughout human history, crystals have held power over our imagination. Ancient Egyptians buried their dead with crystal amulets for protection. Pharaonic tombs have yielded thousands of amulets carved from crystalline minerals, including lapis lazuli, carnelian, turquoise, and rock crystal, each type associated with specific protective or transformative powers that the ancient Egyptians believed would help the deceased navigate the afterlife. The heart scarab, among the most important funerary amulets, was often carved from green stone representing rebirth and placed over the heart to prevent it from testifying against the deceased during the judgment before Osiris, while crystal amulets in the form of eyes, pillars, and sacred symbols were distributed throughout the wrappings and burial goods. These beliefs reflected a worldview where the material properties of crystals, their color, transparency, and durability, connected to spiritual forces and could influence fate when properly invoked. Stones guarded the dead. Crystals opened doors between worlds. Roman nobles cooled their hands with crystal bowls on hot summer days. Wealthy Romans reportedly held spheres of rock crystal, known as crystallum in Latin, to experience the coolness of stone against their skin during Mediterranean summers, exploiting the high thermal conductivity and heat capacity of quartz that makes crystal feel cold long after metal at the same temperature would have warmed. The practice demonstrates both the luxury of owning large pieces of clear quartz in an era before modern mining and the practical appreciation of mineral properties that preceded scientific understanding, with nobles using crystals' thermal properties for personal comfort. Clear quartz bowls also appeared in divination practices, and as symbols of status, their value enhanced by the difficulty of obtaining large, flawless specimens and the laborious process of grinding and polishing such hard material to spherical perfection. Luxury sought the cool of stone. Wealth held clarity in its hands. Medieval Europeans believed amethyst could prevent drunkenness. The very name amethyst derives from the Greek amethystos, meaning not intoxicated, reflecting the ancient belief that wearing or drinking from vessels made of this purple quartz would protect against the effects of alcohol, a superstition that persisted through the Middle Ages and contributed to the stone's popularity among clergy. Greek mythology attributed this property to the god Dionysus, claiming that the nymph amethyst was turned to white quartz by the goddess Diana to protect her from Dionysus's advances, and the remorseful god poured wine over the stone, staining it purple and imbuing it with power to prevent intoxication. Medieval bishops wore amethyst rings partly to symbolize their sobriety and spiritual clarity, and the stone remained associated with temperance long after rational minds rejected the literal power to prevent drunkenness. Names carry old beliefs. Purple stone promised clear heads. Crystal balls were once used by fortune tellers, claiming to see the future. The practice of scrying, or seeking visions in reflective surfaces, employed crystal balls because their clarity and spherical perfection created a meditative focus point that practitioners believed could reveal hidden knowledge or future events to those with the gift of second sight. Genuine rock crystal balls were extremely expensive and required flawless quartz spheres of considerable size, so many scryers used glass or obsidian instead, though the most prestigious fortune tellers insisted on natural quartz for its supposed spiritual properties that manufactured glass could not replicate. The image of a fortune teller gazing into a crystal ball has become a cultural cliché, appearing in countless films and cartoons, yet the underlying human desire to glimpse the future persists today in various forms, from astrology to economic forecasting. Clarity invited visions. spheres focused hope and fear. The fascination with crystal healing has endured for thousands of years. From ancient Sumerians grinding lapis lazuli for magical potions, to modern wellness practitioners placing crystals on chakra points, the belief that crystalline minerals can influence health and well-being has persisted across cultures and millennia with remarkable consistency, despite the absence of physical mechanisms that could explain such effects. Different crystals are assigned different properties by healing traditions, with rose quartz associated with love, amethyst with calm, and black tourmaline with protection, creating elaborate systems of correspondence that practitioners study and apply in therapeutic contexts. The appeal of crystal healing likely reflects multiple factors, including the genuine beauty and tactile pleasure of handling fine minerals. The placebo effect's well-documented ability to influence subjective experience, and the human tendency to seek patterns and meaning in the natural world. Beauty invites belief. Wonder persists without proof. While crystal healing lacks scientific evidence, the practice persists worldwide. Multiple well-designed studies have found no evidence that crystals produce effects beyond placebo, with participants unable to distinguish between real crystals and glass imitations when blinded to which they were handling. Yet the practice continues to attract millions of adherents who report benefits ranging from reduced anxiety to improved sleep. The persistence of crystal healing, despite scientific skepticism, illustrates how human health and well-being involve subjective dimensions that controlled experiments may not fully capture, and the ritual, intention, and beauty involved in crystal practices may produce genuine effects through psychological and social mechanisms, even if the crystals themselves are inert. This tension between scientific materialism and lived experience remains unresolved, with advocates and critics often talking past each other, unable to agree on what counts as evidence or benefit. Science measures carefully. Experience knows its own truth. From ancient myth to modern science, crystals continue to reveal their secrets. X-ray crystallography allows scientists to see the arrangement of atoms in crystals. When X-rays pass through a crystal, they diffract from the regularly spaced atomic planes and produce a pattern of spots on a detector that encodes information about the crystal's internal structure, which mathematically minded scientists can decode into a map of where every atom sits within the repeating unit. This technique, developed in the early 20th century by physicists including Max von Laue and William Henry Bragg, earned multiple Nobel Prizes and revealed the atomic architecture of thousands of minerals, metals, and molecules that had been mysterious despite centuries of study. The beauty of the method lies in using the crystal's own regularity as a natural diffraction grating, turning the very property that defines crystals, their ordered atomic arrangement, into the tool that reveals that order to human understanding. X-rays see atoms. Light penetrates to reveal structure. The structure of DNA was discovered using X-ray crystallography. James Watson and Francis Crick famously proposed the double helix model of DNA in 1953, but the experimental evidence that guided their model came from X-ray diffraction images of DNA fibers produced by Rosalind Franklin and Maurice Wilkins at King's College London, demonstrating how crystal physics unlocked the secret of life. DNA forms ordered fibrous structures that diffract X-rays in patterns characteristic of a helix, and the specific dimensions of the helix, including the distance between turns and the diameter, could be measured from the diffraction pattern by researchers who understood the mathematical relationship between crystal structure and diffraction geometry. The discovery of DNA structure revolutionized biology by revealing how genetic information is stored and copied, launching the molecular biology revolution that continues to transform medicine and agriculture. Crystals revealed life's code. Diffraction changed biology forever. Rosalind Franklin's crystal images were crucial to understanding the double helix. The famous photograph, known as Photo 51, taken by Franklin in 1952, showed a distinctive X-shaped diffraction pattern that confirmed DNA's helical structure and provided measurements essential for building an accurate molecular model. Yet Franklin received little credit during her lifetime for this crucial contribution to one of the most important scientific discoveries of the 20th century. Franklin was a meticulous experimentalist who prepared superior DNA fibers and carefully controlled humidity to obtain crystalline samples that diffracted cleanly, bringing the same precision to biological specimens that crystallographers applied to minerals and metals. Her early death from ovarian cancer at age 37, possibly related to X-ray exposure during her research, came 4 years before Watson, Crick, and Wilkins received the Nobel Prize for work that depended directly on her images and measurements. Images tell truths. Recognition sometimes arrives too late. Proteins must be crystallized before their structures can be fully mapped. Determining the three-dimensional shape of a protein, which directly determines its biological function, traditionally required growing crystals of the pure protein large and perfect enough to diffract X-rays cleanly, a process that can take months or years of trial and error testing thousands of conditions before suitable crystals appear. The difficulty of protein crystallization stems from the complexity and fragility of these biological molecules, which fold into specific shapes maintained by weak forces, easily disrupted by changes in temperature, salt concentration, or other solution conditions, making the search for crystallization recipes more art than science. Recent advances in electron microscopy have begun to circumvent the crystallization requirement by imaging individual protein molecules directly, but X-ray crystallography remains important because it can reveal structural details at atomic resolution when good crystals are available. Shape determines function. Crystals unlock biology's mechanisms. Understanding protein crystal structures helps scientists design new medicines. When researchers know the precise three-dimensional shape of a protein involved in disease, they can use computer modeling to design drug molecules that fit precisely into active sites or binding pockets, like keys fitting locks, a process called structure-based drug design that has produced medicines for conditions ranging from influenza to cancer to HIV. The revolution in HIV treatment, for example, depended heavily on crystallographic determination of viral enzyme structures that revealed binding sites where protease inhibitor drugs could block viral reproduction, transforming AIDS from a death sentence to a manageable chronic condition for millions of patients with access to medication. Pharmaceutical companies now routinely solve protein structures as part of drug development programs, using crystallography alongside computational methods and biochemical assays to understand how potential drugs interact with their molecular targets. Shapes suggest solutions. Crystals guide drug designers. Scientists have grown crystals in the microgravity of space. The International Space Station and other orbital platforms have hosted hundreds of crystal growth experiments because microgravity eliminates convection, the fluid flow caused by density differences that disturb growing crystals on Earth and limits their perfection by introducing defects and irregularities. Without gravity pulling denser fluid downward as it forms around a growing crystal, molecules can approach the crystal surface from all directions equally, potentially producing more ordered and homogeneous crystals than earthbound laboratories can achieve despite their sophisticated temperature and vibration control systems. NASA and other space agencies collaborate with universities and pharmaceutical companies on space crystallization experiments, seeking practical benefits that could justify the enormous cost of growing crystals in orbit. Zero gravity grows perfection. Space removes disturbance. Crystals grown in space can be more perfect than those grown on Earth. Protein crystals grown in microgravity often show reduced defects and improved diffraction quality compared to their earthbound counterparts, producing clearer structural information that can distinguish between alternative models of protein conformation or reveal subtle features obscured by disorder in lower quality crystals. The improvement varies between different proteins and crystallization conditions, with some showing dramatic enhancement in space, while others benefit little, making prediction difficult and motivating continued experimentation as access to orbital facilities slowly expands. Critics argue that advances in earthbound crystallization techniques continue to close the gap, questioning whether the expense of space experiments remains justified, while advocates point to specific cases where space crystallization revealed structural details impossible to obtain on Earth. Gravity introduces imperfection. Orbit offers clarity. Space-grown crystals may lead to breakthroughs in medicine and materials science. Beyond improving structural analysis, space crystallization experiments explore whether microgravity could produce materials with properties superior to Earth-grown equivalents, potentially justifying industrial production in orbit for applications where quality improvements translate directly to value, such as semiconductor crystals for advanced electronics or pharmaceutical compounds requiring extreme purity. Some proteins have proved nearly impossible to crystallize under earthbound conditions, yet form usable crystals in space, opening doors to structural analysis of drug targets that would otherwise remain mysterious and potentially leading to medicines impossible to design without microgravity-grown crystal structures. The long-term vision includes eventual manufacturing facilities in orbit dedicated to producing materials whose properties justify the cost of space production, though current economics limit orbital crystal growth to research and demonstration rather than commercial production. Space crystallizes futures. Medicine may grow in orbit. Some crystals can store data more densely than any current technology. Researchers have demonstrated writing data into transparent crystals using focused laser pulses that create tiny modifications to the crystal structure, potentially storing hundreds of terabytes in a single disk-sized piece of quartz, with longevity far exceeding magnetic hard drives, optical disks, or tape that degrade over decades. The modifications can occur at multiple depths within the crystal and at multiple angles, creating a three-dimensional storage medium where data density far exceeds the essentially two-dimensional surface storage of conventional optical disks. Current prototypes remain laboratory demonstrations rather than practical products, requiring expensive equipment to write and read data, but continued development could eventually produce archival storage systems for libraries, governments, and corporations needing to preserve critical data for centuries or longer. lasers write in crystal. Information awaits the distant future. Five-dimensional data storage in quartz crystals could preserve information for billions of years. The 5 dimensions refer to 3 spatial coordinates plus 2 optical parameters, polarization and intensity of the induced modifications, allowing multiple independent data channels to occupy the same volume of crystal and pushing storage density far beyond what 3-dimensional approaches could achieve with current technology. The thermal and chemical stability of quartz means that data written into its structure would survive conditions that would destroy paper, film, and electronic storage within decades, potentially preserving human knowledge through climatic catastrophes, civilizational collapse, or even the death of our sun billions of years hence. Researchers have demonstrated the concept by recording famous texts and images into quartz disks that could theoretically be read by any sufficiently advanced future civilization, creating time capsules that might outlast humanity itself. Quartz remembers forever. Our words could outlive stars. These gentle facts have carried you this far. Let the wonder settle in without effort. Your breath can deepen now, slow and quiet, like water cooling in a cavern beneath the earth. And in the smallest corners of nature, crystals still surprise us. Ice is a crystal, and no 2 snowflakes are truly identical. Water freezes into crystalline ice with a hexagonal structure that gives snowflakes their characteristic 6-fold symmetry, and the infinite variations in temperature, humidity, and air currents that each falling snowflake encounters during its descent create branching patterns so sensitive to conditions that no 2 natural snowflakes have ever been observed with identical architecture. The statement that no 2 snowflakes are alike has been repeated so often it has become cliché, yet the physics behind it remains genuinely remarkable, because each snowflake's journey through the atmosphere inscribes a unique history of conditions into the growing crystal's shape. Laboratory conditions can produce essentially identical snowflakes by controlling all variables precisely, but natural snowflakes tumble through air too chaotic and variable to repeat the same growth history twice. Each flake writes weather in ice. Falling crystals record atmospheric journeys. A single snowflake may contain 10 quintillion water molecules arranged in crystalline form. This number, approximately 10 followed by 18 zeros, represents more molecules in a single small ice crystal than there are grains of sand on all beaches of Earth. Yet these vast multitudes arrange themselves into the precise hexagonal lattice with perfect coordination, each one knowing its place without external instruction. The lattice emerges from hydrogen bonding between water molecules, which pulls each molecule into a tetrahedral arrangement with its neighbors. And when this pattern extends in 3 dimensions, the result is the hexagonal crystal structure that manifests at macroscopic scales as 6 arms of a snowflake. Consider drawing 10 quintillion tiny dots on paper, and now imagine those dots spontaneously arranging themselves into a perfect lace pattern that would make the most skilled artisan weep with envy. Multitudes find order. Billions dance together. Salt crystals are cubes, shaped by the way sodium and chlorine atoms bond. Table salt consists of sodium chloride crystals that naturally form perfect cubes because the bond between positively charged sodium ions and negatively charged chloride ions creates a cubic lattice where each sodium has 6 chlorine neighbors and each chlorine has 6 sodium neighbors, extending in 3 dimensions with perfect regularity. If you look closely at grains of table salt, you will see tiny cubes, some with stepped edges where layers did not grow completely, but all reflecting the underlying cubic symmetry of the ionic bonds that hold them together. This is why salt crystals crunch between your teeth with a particular texture that differs from the hexagonal crystals of sugar or the monoclinic crystals of baking soda, because crystal shape determines mechanical properties. Chemistry dictates geometry. Bonds build boxes. Sugar crystals under a microscope look like tiny pillars of glass. Sucrose crystallizes in the monoclinic crystal system, forming prisms with slanted ends that glitter brilliantly under polarized light microscopy, revealing internal optical properties quite different from the cubic symmetry of salt, despite both appearing as white powders to the naked eye. The shape of sugar crystals affects how quickly they dissolve, how they feel on the tongue, and how they behave in cooking, with confectioners manipulating crystallization conditions to produce everything from large rock candy crystals to the fine powder of icing sugar. Growing sugar crystals from saturated solutions is a popular science project for children because the process is safe, the results are edible, and the principles of crystal growth become tangible when you can watch and later taste the results. Sweet geometry grows slowly. Patience makes candy crystalline. Chocolate must crystallize correctly to have a satisfying snap. Cocoa butter can crystallize in 6 different forms, only one of which produces the shiny surface and clean breaking characteristic of properly tempered chocolate, while the other forms create a dull, crumbly, or waxy product that melts unevenly and may develop white bloom as unstable crystals transform over time. The desirable form, 5 crystals, are smaller, more tightly packed, and melt at just the right temperature slightly below body heat, which is why good chocolate snaps cleanly at room temperature and then melts smoothly on your tongue, releasing flavor compounds in a controlled progression. Chocolate that has been stored improperly may have converted to less stable crystal forms, explaining why the same chocolate can taste different depending on how it has been treated between factory and mouth. Texture is crystalline destiny. Snap signals proper structure. The art of tempering chocolate is the art of controlling crystal formation. Chocolatiers temper chocolate by carefully managing temperature during cooling and working, first melting all existing crystals, then cooling to a temperature that favors form 5 nucleation, then slightly warming to melt out any unwanted crystal forms while preserving the desired seeds that will guide final crystallization as the chocolate sets. The process requires precision and practice, with experienced chocolatiers reading the texture and shine of the chocolate to know when proper tempering has been achieved, a skill that machines can replicate, but that remains valued as a craft when done by hand. A tempered chocolate bar demonstrates that the principles governing crystal growth in geological environments apply equally in the kitchen, and that understanding crystal physics can elevate cooking from simple chemistry to precise art. Temperature rights in cocoa butter, craft controls crystal. Even time itself is measured by the steady pulse of crystals. Atomic clocks use the vibrations of cesium atoms in crystalline arrangements. The international definition of the second is based on the vibration frequency of cesium-133 atoms, specifically 9,192,631,770 oscillations of the radiation corresponding to the transition between 2 hyperfine levels of the cesium ground state. Atomic clocks achieve their extraordinary accuracy by confining cesium atoms in traps often created within crystalline structures that provide the stable electromagnetic environments needed to measure these oscillations without disturbance from external fields or thermal motion. The resulting timekeeping precision enables technologies from global navigation to financial trading that depend on synchronization across continents, all resting ultimately on the predictable behavior of atoms held in crystalline embrace. Atoms tick precisely, crystals steady the clock. The most accurate atomic clocks lose less than 1 second over billions of years. Optical atomic clocks using strontium or ytterbium atoms trapped in crystalline optical lattices have achieved accuracies where the clock would neither gain nor lose a full second over the entire current age of the universe. A precision so extreme that these clocks can detect the gravitational time dilation caused by raising them a few centimeters above the ground. At this level of precision, clocks become tools for fundamental physics research, potentially revealing subtle effects predicted by general relativity or variations in fundamental constants that would be invisible to any less accurate instrument. The technology continues to improve, with each generation of atomic clocks pushing precision further and opening new possibilities for tests of physics and practical applications in navigation, communication, and measurement. Precision approaches eternity. Time keeps its own counsel. Every GPS satellite relies on crystal oscillators to determine your location. The Global Positioning System calculates position by measuring the time delay between signals arriving from multiple satellites, a process requiring timing accuracy of nanoseconds because light travels 30 centimeters in 1 nanosecond and position errors scale directly with timing errors. Each GPS satellite carries multiple atomic clocks and crystal oscillators that maintain time synchronization with ground stations and with each other, ensuring that the signals stamped with transmission time can be compared with sufficient precision to triangulate a receiver's position anywhere on Earth. Your smartphone performs this calculation dozens of times per second when navigation is active, using signals that have traveled 20,000 kilometers from satellites where crystals vibrate in the vacuum of space. Satellites keep time with crystals. Your position emerges from precision. Without crystals, modern navigation and communication would be impossible. Every smartphone, radio, television, computer, and satellite depends on crystalline components. From the silicon chips that process signals to the quartz oscillators that generate clock frequencies to the piezoelectric transducers that produce and detect sound waves, and the liquid crystal displays that present information to our eyes. Remove crystals from modern technology, and you would eliminate not just smartphones, but also medical imaging, airline navigation, weather prediction, financial trading, and countless other systems that depend on the precise, predictable properties that crystalline materials provide. The hidden ubiquity of crystals in technology makes them easy to overlook despite their essential role in nearly everything electronic. Civilization runs on crystals. The invisible infrastructure sparkles. Crystals are found on every continent and in every geological environment. From Antarctic ice caves containing massive calcite formations to the salt flats of Bolivia, where entire landscapes sparkle with crystalline crusts. From Hawaiian lava tubes lined with mineral crystals to the frozen caves of Greenland, where ice assumes strange crystalline forms. Crystals grow wherever conditions permit atoms to arrange themselves in ordered patterns. Desert environments produce evaporite crystals as mineral-laden water evaporates, while hydrothermal vents on the ocean floor precipitate exotic minerals unknown on land, and even the upper atmosphere contains ice crystals that create halos and sundogs when sunlight passes through them. The universality of crystalline order reflects the fundamental tendency of matter toward its lowest energy state, which in many chemical systems means the ordered arrangement of atoms that defines a crystal. Crystals colonize every environment. Order emerges everywhere. New minerals and crystal forms are still being discovered every year. The International Mineralogical Association approves approximately 50 to 100 new mineral species annually. Crystals with chemical compositions or atomic arrangements never previously documented, many discovered in exotic geological environments or through careful re-examination of museum specimens collected long ago. Some new minerals come from meteorites containing crystal forms that cannot exist under earthly conditions, while others emerge from mine tailings where human activity has created chemical environments without natural analogues, producing crystals that would never have formed without our intervention. The continuing discovery of new crystalline forms reminds us that despite centuries of mineralogical study, the crystalline world retains secrets waiting to be revealed by patient observers with the right tools. Discovery continues forever. Hidden forms await recognition. The study of crystals continues to unlock secrets about the universe itself. Crystallography has contributed to breakthroughs in fields ranging from materials science to structural biology, and the techniques developed for studying earthly crystals now help astronomers identify minerals on distant planets and moons through spectroscopic signatures that reveal crystalline compositions across cosmic distances. The same principles governing how atoms arrange themselves in crystals on Earth must apply throughout the universe, making crystal physics a literally universal science that connects laboratory experiments to observations of stars and galaxies. As our instruments improve and our understanding deepens, crystals will continue revealing insights about matter, light, and the fundamental forces that shape reality at every scale from atoms to worlds. Crystals teach universal truths. Pattern connects everything. And so our journey through the sparkling world of crystals draws softly to a close. We have wandered through caverns where giants of gypsum touched the ceiling, held the mathematics of snowflakes in our imagination, and traced the hidden crystalline architecture within our own bones. From the ancient Greeks who mistook quartz for eternal ice, to the scientists who use crystals to decode the secrets of life itself, we have followed the quiet geometry of atoms arranging themselves into wonder. If this journey through hidden structures and patient growth has brought you peace, consider subscribing or sharing this space with someone who needs a restful night. There are more wonders waiting to be explored, more gentle facts to carry you into stillness. Right now, as you lie here, crystals are forming in the darkness beneath the earth. In your watch, a tiny quartz is vibrating 32,000 times each second. In your teeth and bones, mineral lattices hold you together with quiet strength. You are surrounded by crystals, held by them, measured by their patient ticking. If your eyes feel heavy, let them close. Let the tension drain from your jaw, your shoulders, your hands. Breathe slowly and deeply, imagining each breath as the slow deposition of atoms, one upon another, building something peaceful within you. Let your body grow heavier, settling into the surface beneath you like sediment drifting to a cavern floor. Tonight, as you sleep, crystals will continue their silent work. Deep in the earth, new patterns are forming. In laboratories, scientists are growing perfect lattices for technologies not yet imagined. Snowflakes are crystallizing in distant clouds. The world is full of hidden geometries, and you are resting within their quiet embrace. You are a small, warm presence among the glittering architecture of nature, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that even the most perfect forms emerge from patience, that beauty can grow in darkness, and that you, like a crystal, are shaped by time and the slow accumulation of moments. This has been Drowsy Discovery. Good night.